We did a few examples. We did some examples last time where we looked at one CSTR and we calculated G tilde, 1 plus ST. This was a CSTR with a first order reaction. We calculated G tilde by omega, and then we calculated the magnitude of G tilde omega as B over A, and phi was the arctangent of the imaginary part over the real part, which just gave me the arctangent of minus omega t. We also did the case of two CSTRs in series where they were the same, of the same volume. This is V1 equals to V2. And we found G tilde was equal to Kp2 over 1 plus St squared. And we found B over A was 1 over 1 plus omega squared. Let's make these T. This is tau. And this is T squared. And phi was the arctangent of 2 omega t over 1 minus omega squared t squared. I just worked out if V1 is different from V2, then we have that G tilde of S is equal to 1 over 1 plus K tau 1, 1 over 1 plus K tau 2, where this thing and this thing are the steady state gains of the first reactor and the second reactor, divided by 1 plus ST1, 1 plus ST2. So obviously that's clear, the generalization from here. And then we found that B over A was equal to 1 over the square root of 1 plus omega squared T1 squared, T, 1 over the square root of 1 plus omega squared T2 squared. And phi is the arctangent. Did I work it out? Did I bother working it out? Well, no, you have to go through the details. Again, it's the imaginary part over the real part. And how do I get the imaginary part and the real part? I plug in for S I omega. So, and that so here I would have Kp1, Kp2, those are just constants. And here I would have 1 over 1 plus I omega T1, 1 plus I omega T2. And I would have to multiply, just as I did here, by 1 minus I omega T1 over 1 minus I omega T1. And 1 minus I omega T2 over 1 minus I omega T2 to get the i's out of the denominator and into the numerator. And what you would find, if you go through that algebra, is G tilde of I omega, for this case, would be equal to 1 minus I omega T1, 1 minus I omega T2, divided by 1 plus omega squared T1 squared, 1 plus omega squared T2 squared. And then, of course, you'd have to multiply this out to get the real and the imaginary part. I guess I could do that. So what you get is G tilde of I omega, this is for the two CSTRs in series, would be equal to, I've got the denominator, 1 minus omega squared T1 squared plus 1 plus omega squared T2 squared. And the numerator would be 1 times 1 is 1. And then I have minus I omega T1 times minus I omega T2. Minus and minus is a plus. I squared is a minus, so minus omega squared T1 T2. And then I have minus I times omega times T1 plus T2. So the phi in this case would be the arctangent of the real part over the imaginary, part over the real part, both the imaginary part, this over the denominator, and the real part, this over the denominator, have the same denominator. So I would just have minus omega t1 plus t2 divided by 1 minus omega squared t1 t2. So that would be the case for two CSTRs of different sizes. Before I just go on to the next thing, I want to introduce something called Baudet diagrams. Now, for now, these are essentially just graphical versions of what we have already. So, but as we'll see later on when we're doing control, the Baudet diagrams will help us do control. But right now they're just they're just graphs. So, for example, for one CSTR with the first order reaction, and remember that B over A is equal to this quantity. So let's plot the log of B over A versus the log of omega. So let's see what happens. And this is called the Baudet plot. So notice that this is equal to, well, let's see what happens when omega is 0. When omega is 0, this thing goes to 1. Well, omega 0 means log of omega is minus infinity, so I'm never going to get there. But if I have a 1 here, then clearly this is going to be heading towards 1. But what happens at the other part? When omega is big, then I can forget about the 1. And the square root of the square is 1 over omega t. So if I have the log of 1 over omega t is minus the log of omega. So it looks like it's just this thing should look, the log of B over A should, at log omega, should just look like minus log omega, meaning it should have a slope of minus 1. So that's what it looks like by plotting this equation, this graph here. The other one, so that's the first Baudet plot, and the other one is to plot phi versus log omega. So let's look at phi versus log omega. All right, so phi, for first order reaction, it's the arctangent of minus omega t. Let's just look what the arctangent looks like. So here's 0, here's pi over 2, and here's minus pi over 2. If I want to look at the arctangent of phi, remember the tangent is the sine over the cosine. So the tangent of 0 is 0 because the sine is 0. So the arctangent of 0 is 0. On the other hand, the tangent is the sine over the cosine. When phi is pi over 2, the cosine is 0, and the sine is 1. So 1 over 0 is kind of plus infinity, kind of the limit. And similarly, at minus pi over 2, I'm getting 0 over minus 1. So it looks like minus infinity. So if I plot the arctangent, I get something that looks like this. All right, so that tells me what I can do here. So when omega is 0, so that's way out here, way out there. When omega is 0, the arctangent of 0 is 0. So if this is 0, I get to 0. It's going way out to 0. It's trying to get to 0. I never get there because I have the log of omega. I need to go minus infinity. However, when omega goes to infinity, minus omega t goes to minus infinity. So the arctangent of minus infinity goes to minus pi over 2. So if this is minus pi over 2, it looks like that. So these are Baudet diagrams, which, you know, just for fun, because we like to do graphing, they're just for fun now. Later on, they'll be useful. But right now, they're just for fun. Are there any questions? So other than the Bode diagrams, everything was reviewed so far. Again, if there's anything you don't understand, ask questions. For those of you who walked in around 10, 11 o'clock and saw people sitting here, let me remind you, I'm coming 45 minutes before every class, so at 10:15, to answer questions. No new material. If there's anything you don't understand, that's a really good time to ask questions, because chances are any question you have, other people have the same question. Okay, so what I want to do is just sort of collect some canonical examples. When I say canonical, I mean when you have the same equation coming up in from many different problems. You just sort of say, it comes up all the time, let's call it a canonical example. So, for example, there are first order systems. And I can represent all first order systems in the form t dy dt plus y equals kp. Do I want to call that kp? Times kpx, sorry. Well, where did I get that from? Remember, if I had one CSTR, that's of that form, because the CSTR was dCA dt plus CA is equal to 1 over tau CA in minus CA minus KCA. So if I move this to the other side of the equation, I have dCA dt plus K plus 1 over tau CA is equal to CA in over tau. And let's note that we call this thing 1 over t. The t now is tau over 1 plus k tau. I did this algebra a million times. So now, if I just multiply through by t, I get t dCA dt is equal to, I multiplied through by t, so I don't need that. I have plus CA is equal to CA in times t over tau, where t over tau is 1 over 1 plus k tau. And now this is exactly this form. And I want you to notice that this is kp, because as we've shown various times this semester, this is the steady state result of CA over CA in. And you probably saw that by now in your kinetics class also for a first order reaction. So this is of that form. And we've done all the algebra on this one. But just for fun, we'll just remind you a little of it. So we can notice when we Laplace transform, so I'm repeating the same algebra. When I Laplace transform, I have st plus 1 times y prime tilde. Let's assume that, I'm assuming that all the variables now are prime. The y's and the x's are prime, without me bothering to write it. They're all prime variables. Is equal to kp x tilde, or y tilde is equal to kp x tilde over 1 plus st. And g tilde, which is y tilde over x tilde, is equal to kp over 1 plus st. And of course, if I do an inversion, so if I have a step, then x tilde is just equal to delta x over s. And in that case, I have y tilde is equal to kp x delta x over s 1 plus st. This s comes from here, the 1 plus st comes from here. And when I invert from, I think it's line 5 in the table, this is algebra we've done before, so you don't really need to copy it. When I invert, I just get kp delta x times 1 minus e to the minus t over big T. And you can notice, for example, that as t goes to infinity, I just get kp delta x. And of course, I guess I could put the primes in just to be consistent, since I've been doing it all along. So we can notice that y prime tilde over, y prime of t over delta y over delta x as at infinity, as t goes to infinity. As t goes to infinity, delta y is y prime, delta x is just kp, which is 1 over 1 plus, which in this case is 1 over 1 plus k tau. Let's see a pulse. For a pulse, x prime tilde is just a constant. It's a pulse. It's just the amount of stuff you dump in that was in the bucket, the amount of A that was in the bucket. So in this case, y prime tilde is equal to kp times m over 1 plus st. So I look at this guy, where is it? This guy, and for x prime I just plug in m. There's no other s. And then when I invert that, I have y prime of t, and this is line 4. From line 4, I just get 1 over t, so I have kp m divided by t, e to the minus 0 over big T, which as t goes to infinity, gives me 0. And I could have seen that from the final value theorem. From the final value theorem, I know that the limit as t goes to infinity of y prime of t is the limit as s goes to 0 of s y prime tilde. Well, s times this gives me an s in the numerator. When I take s goes to 0, I get 0, as I should. In this case, when I multiply by s, the s's cancel. When I take s goes to 0, I get kp delta x, which is exactly what I found here. Finally, if I look at the frequency response, so there are people who don't seem to want to come on time, and then they complain when they don't understand the material. But at least they come. There are people who don't come. Okay, and if I want the frequency response, then of course I need G. Here's G. And I can note that B over A is the magnitude of G tilde by omega, which is the magnitude of Kp over 1 plus I omega t, which we worked out already. I'm not going to bore you with that. And phi is the arctangent of the imaginary part over the real part of G tilde by omega. And again, that's the imaginary part of the real part of this thing, which again, I'm not going to bore you by repeating the same algebra I've just done. So really all I've done is I've repeated the algebra for one CSTR. Or if nothing else, I just put it all in one place. Now why have I done that? I've done that because I want to go to a second order system. So let's go to a second order system. Now the simplest second order system is 2 CSTRs in series. The simplest one is 2 CSTRs in series. So let's just look for that one. And I want to do that using this notation. So here I have, say, T1, dy1 dy1 prime dt. plus y1 prime is equal to kp x in prime, x prime. And let's look at, for T2, I've got T2 dy2 prime dt plus y2 prime is equal to kp 2 y1 prime. And let's just, so this is reactor 1, and this is reactor 2, because you have X going into reactor 1, but you've got the output from reactor 1, Y1, going into reactor 2. Now, to show you that this is I've never formally shown you that this is a second order system. Second order means two derivatives, not one. So one way of doing that is I can just plug in from here for Y1. Right? Yeah, I can do that. Yeah, so let's multiply the first one by kp2. So I have kp2 t1 dy1 prime dt plus y1 prime is equals to kp1 x prime. And now on the right hand side, I have kp2 kp1 x prime. But on the left hand side, I've got kp2 times, I've got t1 times ddt of kp1 y1. ddt, I'm sorry. Yeah. So on the left hand side, I've got a t1 times ddt of kp2 dy1 dt. Did I do that right? kp2, or was I going to do it the other way around? Okay, so I have dy1 dt. Yeah, so I have dy1 dt. I want to take ddt of this. Yeah, so here I have a ddt of kp2 y1. Here's kp2 y1. So I want to take ddt of this to plug in for these two. So when I take ddt of this, I get a t2 times d squared y2 prime dt squared plus dy2 prime dt. So again, what did I do? I took the t1 out, and I have kp2 y1 prime. I want to take the derivative of that. Here is kp2 y1 prime. I take the derivative of that. I take the derivative here. So I've got a second derivative here and a first derivative here. And now I have plus y2 prime. I'm sorry, plus y1 prime. Plus kp2 y1 prime. So that's plus all of this. Let's move this over. So plus kp2 y1 prime. That's equal to t2 dy2 prime dt plus y2 prime is equal to kp2 kp1 x prime. Is that clear, the algebra that I did? I have two equations. I want to combine them. So I multiply the first one by kp2. And when I multiply the first one by kp2, I have a kp2 y1. kp2 y1, I know what that is. That's this. So I just copied that here. And here I have t1 times ddt of kp2 y1. t1 times ddt of kp2 y1 times ddt of this, which is that. So, you have to pull your mouse down.
Why is an x on the right-hand side of the top equation and a y on the right-hand side?
Why is x on the right side?
Of the top equation, and then a y on the right-hand side.
Okay, that I think thought we went through that. When we have two CSTRs in series, what's entering the first reactor is x, and what enters the second reactor is what comes out of the first reactor. So what comes out of the first reactor is y1. Okay, it would be nice if you guys came on time. You really can't expect to understand what's going on if you come a half hour late. You know, people tell me, oh, the train was late. But it's late every day, so you have to leave the house earlier. Okay, So let's rewrite this. So I have t1, t2, d squared y2 prime dt. So I've got a second derivative plus t1 plus t2 dy2 prime dt plus y2 is equal to kp2 kp1 x prime. So here we have a second order reaction with a second order system, and now you know why I call it second order, because there's a second derivative. There are no more y1s here. It's second order, there's two derivatives, one derivative, and no derivatives. And we know the result of this. We know that I'm going to get, well, if I do, I know I'm going to get roots that I know my denominator, because this is two CSTRs in series, we've already done it, is going to have a 1 plus ST1 in it and a 1 plus ST2. And we also know that I'm going to get a KP1 and a KP2. I just did it over there. KP1 and KP2. Where KP1, which are the long time solutions here. And I'm thinking this is going to be my G tilde of this. Okay, why do I bring this up? Well, I want to remind you of something. I want to go back to freshman physics. Because, as it turns out, so many ideas and so many advanced courses in physics or engineering all come back to freshman physics. So, let's do a little aside in freshman physics. Remember you had a problem in freshman physics of a spring with a block on it. You remember this problem? With K. What's Newton's second law? Someone want to remind me of Newton's second law?
Force equals mass times acceleration. Force equals mass times acceleration.
Force is mass times acceleration. So I have the mass m times x double dot. The acceleration is the two derivatives. And then I have the force. What's the spring force? Somebody else? What's the spring force? Should I call them people? How about the people who come late? One of you all the way in the back. What's the spring force? I want the form of the spring force. You have to pull your mass down.
The formula is it's
Kx squared.
You talk about the formula.
What is the force of a spring? Come on, this is. Did you take freshman physics? Okay. What is the person next to you? What is the spring force? Hello? What is the spring force? What is the spring force? If you're having trouble with that, I don't know how you're going to handle this course. K times x minus kx. So that one is a second order equation, but let's say I introduce friction. Let's say the block has some friction with the base. So what's the form of the friction term? Remember from freshman physics? What's the form of the friction term? What is the friction proportional to?
Velocity? To the velocity?
To the velocity. Is it increasing, is it accelerating or decelerating?
So
Is it making it go faster or slower?
makes it go slower.
Makes it go slower. So I have minus some friction constant times the velocity. And now we have something physical here. We know that this term slows down the motion of the block because it's friction. So this term is called the damping term because it's damping the motion. So if we rewrite this equation, it's mx double dot plus cx dot plus kx equals 0. So when we see an equation like this, the coefficient of the first derivative is a damping term. It's damping. It slows things down. Now let's go back to this problem. Here we have t1, t2, we have a second derivative, a first derivative, no derivative. Now by the way, here Well, if I start pushing the block, if I push the block, then I'll get something on the right side. But here I have the 0. I'm not worrying about that. In our problem, we have something pushing, x prime, the forcing function. But you can imagine that this term could have a physical interpretation as some sort of damping. Let's see why that would be the case. If you remember, we plotted some things earlier in the semester. If we looked at x prime of t, if this was a step function, and then we looked at y1 prime, the output of the CSTR versus t, we saw that that thing looked like this. And if we looked at y2 prime, of t, then that thing, so here's 0, 0, 0, that thing changed more continuously. So we notice that here x prime was discontinuous, here y1 prime was continuous, but its derivative was discontinuous. And here, even the derivative was continuous. Y2 prime, the second derivative was discontinuous. So it doesn't automatically change slope. It goes from second derivative 0 to non-zero second derivative. So you can see that there's some sort of damping here of the output versus the input. Okay, well, let's, motivated by this, let's write out what we would call a general second order system. A general second order system, not restricted to coming from two CSTRs in series or two first order systems in series. So I can write a general one as t squared e squared y dt squared. I'm using t squared, right? T, yes. Plus 2c t dy dt plus y prime equals x prime. And let me just make sure that's exactly the form that I want. I need a KP. A KP. Now, this is a little more general. First of all, this looks just like this, but there's a forcing function. And notice there isn't, whereas over here, there is a strict relationship between the coefficient of the second derivative and the first derivative. If I know t1 plus t, these aren't arbitrary numbers, they're related. Whereas here, they're not related, because c can be anything. So that's why this is more general. Okay, so why don't we go ahead and try to solve this one. So let's solve it. Again, because the prime variables have 0 initial condition, when I take the derivative of this, I'm just going to get 2ct s y prime tilde. This I'm just going to get y. Normally, the Laplace transform of the derivative is s times y prime tilde minus the initial condition. The initial condition is 0 because they're prime variables, so I don't need that. On the right-hand side, I've got kp2 x prime tilde. And on the left, I'm going to assume that the initial condition not only of y prime, but of its derivative is 0. In that case, each of these is going to give me an s squared. Now that's because we assume, or we set up, that y prime of 0 is 0, and dy prime dt at t equals 0 is 0. So that way I don't have initial conditions coming in. I can factor out the y prime tilde. And that's equal to kp2 x prime tilde divided by a polynomial. 1 plus 2cts plus t squared s squared, which is a polynomial in s. Well, that's okay. I like polynomials. Why do I like polynomials? Because remember, this semester we were looking at Laplace transforms that were ratios of polynomials, n tilde over d tilde. So here I have d tilde as a quadratic equation. Okay, now I'm going to ask you a really hard question that goes all the way back to 9th grade. I want to find the roots of the zeros of the denominator. So S star is equal to. So who remembers the quadratic formula? Somebody else. Thank you. I know. Somebody else who has an answer. Who remembers the quadratic formula? Miss? Yeah. What's the quadratic formula? Can we apply the quadratic formula to this? You have to pull your mask down. I can't hear anything. I don't know what A and B are. You have to do it in terms of this equation here. Here's an equation. I'm asking you something literally from 9th grade. Please apply the quadratic formula. Okay, I'm sorry, we don't have time. Can someone not volunteer for the quadratic formula? Somebody in this crowd, yes?
So, plus or minus 2,
Why don't we start from the minus b part?
minus 2 CT. Plus or minus square root 2 CT squared. Minus 4 times t squared. All over 2 times t squared.
Thank you. Okay, so the first thing is I'm going to distribute the 2 in here. 2 squared c squared t squared. And I'm going to cancel one t in the denominator with these t's. And here I have, and I'm also going to cancel the 2. 2 cancels a 2 here, and it cancels a 4 in here. So I have S star is equal to minus c plus or minus the square root of c squared minus 1 over t. So those are my roots. And let's examine, yes?
How did you get t squared
Where?
in the first term under the square root?
It's over 2a. This is a.
No, in the square root, you have 2 CT, right?
2ct, which I have to square, 4c squared t squared. b squared minus 4a is t squared, c is 1. Got it? So here we have this, and let's notice, remember, from what we did earlier in the semester, c greater than 1, the stability of the system depends on whether the roots have a positive or negative real part. So, and whether the system oscillates as it decays depends on whether it's complex or not, whether there's an imaginary part. So the first thing we can notice here is, here I have c squared minus 1. That's less than c squared. So the square root of c squared minus 1 is less than c. Agreed? So that says, even when I add it to minus c, I can never get something positive real. So this thing, the real part is always negative. So the first part, the real part, always negative. Not even 0, it's negative, because I'm subtracting 1. And c is, here I'm assuming c is a positive number. Okay, so that's the first conclusion I can draw. Now let's look, there could be different values of c. So let's notice, if c is greater than 1, if c is greater than 1, then the discriminant is greater than 1, and the square root is real. So that tells me both S stars, S star 1 S star 2 are both real and negative. In which case the system is stable. It's stable, no oscillations. How about when C is less than 1? If C is less than 1, well then this is, the discriminant is negative. I have an imaginary part, but the real part is still negative. So S1 star, S2 star are complex with the real part less than 0 and the imaginary part not equal to 0. So that tells me that it decays and oscillates. Stable, but it's underdamped. Underdamped again means it decays and oscillates. This one, no oscillation, is overdamped. Who knows why they call it overdamped, underdamped? Who cares? It's just a name. That is, this one decays exponentially, and this one oscillates and decays. And then finally, there's a case C is equal to 0. That's allowed. C is 0. And that's like I have no damping here at all. If I have no damping, then this oscillates forever. So when C is 0, well, this is 0 plus or minus the square root of -1 over t. So S star is equal to plus or minus I divided by t. In other words, I have purely imaginary roots, purely imaginary, and it oscillates. How do I know it oscillates? The roots are purely imaginary, so I have to go to that case where I have complex roots. I have e to the alpha t, alpha 0, that's the real part, times a cosine plus b sine. That is, I get a cosine e to the 0 t times a cosine 1 over t, t over t, plus b sine t over t. So it just oscillates forever. And that is obvious from here. If I say c equal to 0, I just get simple harmonic motion. And A and B depend on the initial conditions. Any questions on that? Well, that's funny. We said that this guy is general and this guy is specific. Let's look at this particular case. So let's go back to our specific case and relate this case to this case. Let's relate them. So notice, let's relate general case to two CSTRs in series, two first order systems in series. Well, in that case, the coefficient of y dy d squared y dt squared should equal this, and the coefficient of the first derivative should be equal to this. So again, you don't have to worry about writing everything down. You're going to get pictures of this. It's more important to listen. So that says, let's figure out what t and c are in terms of t1 and t2. So here I have t squared is t1, t2. So that says that t is the square root of t1, t2. And I have 2ct is equal to t1 plus t2. Meaning c is equal to t1 plus t2 divided by 2t, root t1, t2. You with me? Or against me? Okay, so let's just, for fun, let's square t, back c. C squared is t1 plus t2 squared. It's t1 squared plus t2 squared plus 2 t1, t2. And the denominator is just 2t1, t2. So I just squared the numerator. I think you can notice that t1 and t2 are positive. Here I have 2t1, t2. Here I have 2t1, t2. But here, I'm adding two terms, so this is clearly greater than 1. Because the denominator is the numerator plus other stuff. I can't hear you. You're putting your hand in front of your mouth to make sure I can't hear you.
So you said you squared the whole thing. Should we have a 4 over there? Is it 2?
Yes, I'm sorry. 4. Yes, 4. Let's see, did I make a mistake here? Is that a 2? Let's just make sure that's a 2. Yeah, it's 2. So maybe that isn't as obvious as I thought. 2 root T1, T2. 2. No. Okay, so it's not necessarily greater than 1. Well, that's too bad. I thought that would work out. Just make sure I didn't screw anything up here. So T is, that's correct, 2C times T1 plus T2, is 2, is 4. Okay, I guess we can't conclude what I wanted to conclude. But we do know, or the argument would be a bit more complicated. So here I would have to show that T1 squared plus T2 squared is greater than 2T1, T2. So let's just see. Is T1 squared plus T2 squared greater than 2T1, T2? That I think, okay, yeah, I think I can still show that. Well, T1 squared plus T2 squared minus 2T1, T2 is equal to T1 minus T2 squared. And this is in fact greater than 0. Thanks for pointing that out. So the argument's a little more complicated. So if we look at the numerator, I've got a 2T1, T2 plus T1 squared plus T2 squared. And the denominator, I have 2T1, T2 plus another 2T1, T2. So what I want to check is what I'm adding in the numerator to 2T1, T2 is bigger than what I'm adding in the denominator. So what I'm adding in the numerator is T1 squared plus T2 squared. And what I'm adding in the denominator is 2T1, T2. So the question is what I'm adding in the numerator bigger than what I'm adding in the denominator? Well, so that it says, is this thing bigger than this? Or is the difference bigger than 0? Well, the difference is exactly a perfect square, so it is bigger than 0. So therefore, C is greater than 1. So in the case of two first-order systems in series, I'm always in this situation where it's stable, and we knew that because we had that for two first-order systems in series. We knew it was always stable. We had solved that explicitly. And now we can see why two first-order systems in series are always stable and always overdamped, because they always have C greater than 1. But in the general second-order system, that doesn't have to be the case. I can have C less than 1 as well. Are there any questions on that so far? Okay, well, let's calculate. Let's see, what do I want to calculate here? Yeah, okay, so let's look at the first order system. And so in a first order system, where did it go? Here it went. So in a first order system, so we have G tilde is this. So if we have B over A was KP over this. And let me just remind you that B over A for the first order system was the magnitude of G tilde over I omega. It was KP, and we worked it out over here. It was over the square root of 1 plus omega squared T squared. That was for the first order system. And I want you to notice that B over A, the amplitude ratio, for any value of omega, the denominator is greater than 1. So this is always less than or equal to Kp. It's actually for any finite value, it's always less than Kp. So it's always less than the steady state gain for a step. The amplitude ratio of the output sign over the input sign is always less than, for any frequency, less than the steady state gain of a step function. On the other hand, for the second order system, so I think I have, yeah. So for the second order system, I kind of need to work this out. So let's look for a second order system. And, here, I have it here. No, I guess let's just see what I want to do there. All right, I guess I'll have to work it out. So this is an aside. Is I'd like to calculate the G tilde of I omega for a second order system. And which is B over A. And which system do I want to do this for? I would like to do this, yeah, for a general second order system. Okay, so let's have my general second order system. Actually, it's not even an aside. G tilde is y prime over x prime. So G tilde of s, which is y prime tilde over x prime tilde, is equal to Kp2 over 1 plus 2ct s plus t squared s squared. Okay, and let's calculate G tilde of I omega. There's y prime tilde over x prime tilde at I omega, which I don't need that again. So I have Kp2 divided by 1 plus, and now I need to plug in I omega. So I omega quantity squared, I squared is minus 1. So I've got minus omega squared t squared plus 2 times s is I omega, so 2ct times I omega. 2ct times I omega. So now again, I have an I in the denominator rather than in the numerator. So to get it in the numerator, I multiply and divide by 1 minus omega squared t squared minus 2ct omega I over same thing, t squared minus 2ct omega I. And if I do that, I get Kp2 times 1 minus omega squared t squared minus 2ct omega I divided by some denominator, which I don't even really have to calculate, because this is a plus ib, and this is a minus ib, and that's just going to give me a squared plus b squared. So I can calculate that. It's just 1 minus omega squared t squared squared plus 2ct omega squared. But that's just the denominator. It's a real number and it's a denominator. I can keep it. So now let's calculate the magnitude of G tilde of I omega. Again, for my triangle, real part, imaginary part, if this is the magnitude of G tilde, this is the real part of G tilde, and this is the imaginary part of G tilde. And by Pythagoras' theorem, the magnitude is the square root of the real squared plus the imaginary squared. This is the real square, this is the real part, and this is the imaginary part. So it's the square root. Since they both have the same denominator, I can square them and take the square root. And now I take the square root of this squared plus this squared. So the square root of 1 minus omega squared t squared squared plus 2ct omega squared. And that whole thing now just gives me, the numerator is just the square root of the denominator, 1 over the square root of 1 minus omega squared t squared squared plus 2ct omega squared. And here I have my amplitude ratio. This is B over A. And the only thing I've lost is Kp. So all that work, and I want to contrast the amplitude ratio for a first order system. Where here we have the amplitude ratio for a first order system that was always less than or equal to Kp. Because for any omega greater than 0, the denominator is bigger than 1. On the other hand, for a second order system, we just calculated it. For a second order system, we see that B over A is equal to Kp2 over something. And for some values of omega, I'm subtracting something, omega squared t squared, from 1. This thing is going to be less than 1. And sometimes, for some omega, depending on c, this might not make up for what I'm subtracting. So this could either be bigger or smaller than Kp2. It depends on c. So this can be either bigger or smaller or equal to Kp2. I can't distinguish because for different omegas. Are there any questions on that? Can we take a picture of that blackboard so I can go on? Questions? Okay, again, since I've done all the work, I might as well do this too, is the arctangent of the imaginary part over the real part. Well, here's the imaginary part, here's the real part. So it's minus 2ct omega over 1 minus omega squared t squared, where this denominator is in the denominator of the real part and the denominator of the imaginary part, so I just cancel them. And I have phi is equal to this quantity. Is there any questions on that? I would like to stress to people that there's a significant number of people, every class there are a handful of people who don't come for some reason. In every class there are people who come late enough that they're not going to be able to follow what I'm doing. Now, you're grown-ups. You can do whatever you like. But the material in this class is new. It's not a rehash of old courses. And it's not easy. If you want to understand the material, you have to give yourself the opportunity to understand the material. And that means coming to class prepared to learn. Coming to class prepared to learn means you've reviewed the material from previous classes. Anything you didn't understand, you come during the office hour before class to ask. And you're here for the beginning of class when the people who are here at the beginning of the class realize that I start the class by reviewing the important stuff from the last class and connecting it to what I'm doing in this class. If you miss that, it's like coming in the middle of a movie. You come in the middle of a movie, you don't know what's going on. Anyway, that's a word to the wise. Again, I can't be a policeman. I'm not interested in being a policeman. It's just a strong recommendation I would like you, when you leave this class, to be able to do the basic control, because you might actually need it in your job. And this connects to the real world control. But you have to give yourself the opportunity to learn the material, because it's new. Okay, so we're looking at canonical systems. We looked at first order, second order. Now we're going to look at integrator systems. Now, notice, in the systems we've been working with, we not only had the derivative on the left, we also had the function itself on the left. And we saw, from this particular example, that was the spring force. That's what's pushing it back and forth. That's the spring force. It's not an external force, it's the internal force. Let's see what happens if I don't have that. In other words, if I take dy dt, and that's just equal to kp times x prime. So no more, and I may need a t in there. Do I want a t in there? I think I want a t multiplied by that. Yes. T. And this is not the right-hand side does not depend on y. So let's see what happens here when I leave that one out. Well, if I leave it out, then I get y prime of t is equal to kp over t times the integral of x prime of t prime dt prime from 0 to t. So if y prime is now the integral of x prime, well, that's why we call it an integrator. Well, why is that? Well, let's notice, or what does that mean? What happens if x prime is a step? A step. Well, if x prime is a step, meaning x prime versus t goes like this, where this is delta x. Well, so this now becomes y prime of t is equal to kpt. Now this is a step function, and from 0 to infinity. So this just becomes delta x. It's a constant. It comes out of the integral, and I just have the integral from 0 to t to t prime. In other words, this just becomes kp over t delta x times t. This thing just grows forever. If I have a step input, my output, y prime, here's 0, just goes like that. Goes off to infinity. If I have a pulse, if x prime is a pulse, the area is n, here's t, x prime. So we're 0 before, 0 after, and I just have a pulse. So then I have y prime of t is equal to kp over t times the integral of the pulse. The integral of the pulse is just the area. It's m. I integrate this thing. So notice that in this case, the response to a step is a finite response. Here, the response to a step is an infinite response. Here, the response to a pulse was eventually goes back to where it started. Here, if you introduce a pulse, it never goes back to where it started. It just goes back, it goes to this new value. So y1 versus t equals 0. Before here, there's nothing, and then I integrate this, and it just jumps to a value, and it stays there. So the integrator has a different character. And let's just notice, let's Laplace transform. So I have t y prime tilde times s is equal to kp x prime tilde. So I have g tilde is equal to y prime tilde over x prime tilde is kp over st. And let's see what we can do with this. Let's look at the final value theorem. Let's just verify this. The final value theorem for a step, let's just solve this. Y prime tilde is kp x prime tilde over st. So a step function. So for a step, I have the limit as s goes to 0 of s y prime tilde of s is equal to the limit as s goes to 0 of kp x prime of, this is delta x over s squared t, because x prime tilde for step is delta x over s. And that just is infinity. Yeah, the long-term behavior is infinity. I multiply by s, so one of those cancels. On the other hand, for a pulse, the limit as s goes to 0 of s y prime tilde of s is the limit as s goes to 0 of s times, I've got a kp over st, and x prime tilde, we said for a pulse, is just m. The s's cancel, and this just gives me kp m over t, which is in fact what we found. How about the response to a sinusoidal input? So let's look at the response to a sinusoidal input. Well, we can't look at the response to a sinusoidal input because the assumption when we did our derivation was the system was stable to a pulse. This is to a step. This is not stable to a step. So I can't do my analysis because I violate that I violate what the assumption. But if I did do it and I looked at g tilde of I omega, well, gee, that would be kp over I omega t, which I multiply top and bottom by I, and that just gives me minus kp I over omega t. And the amplitude ratio, if I could calculate it, v over a, would be the magnitude of this, would be kp over omega t. And the phi would be the arctangent of the imaginary part over the real part. But there's only an imaginary part. So if the imaginary part, the real part is 0, the imaginary part is minus 1. So I'm getting minus infinity. And the arctangent of minus infinity is pi over 2. Minus pi over 2. The problem with that is it's not stable. So, and let's just see what, let's just check to see if that's actually right. How do we check stability? I made that statement a little too quickly. Let's check stability. How do I check stability? I look at the roots of the denominator. So, stability. If I look at the denominator of y prime, that's equal to 1 over, the denominator is st. So what are the roots of the denominator? The root is 0, is s equals 0. So this is 0 root. So remember, that's the indeterminate case. It doesn't blow up. This goes to e to the st, it could go as a constant. So since it's not blowing up, remember, when I have, recall, 1 over s minus alpha gives me s e to the, when I invert it, I get e to the alpha t. In this case, when s alpha is 0, I get e to the 0 t. So it's not unstable. So that was not correct what I said. It's not it doesn't go exponentially to 0, but it goes to a constant. We can live with a constant. That's not infinity. or that doesn't make it unstable. With respect to a step function, it will give me an infinite result, but that's as a result of the input. That's not the natural part of the system. That is, the characteristic polynomial is not unstable. So therefore, I can do this. I can come up with an amplitude ratio and a phi. And let's notice what we expect to happen. If my input, x prime versus t, is a sine function, when I integrate the sine function, let's look at because I have to integrate this thing. The integrator, y prime versus t. Well, when I integrate, I start here, and I integrate, it goes up. It keeps going up. So it goes up fast, and it slows down. And then when I get to here, this is at pi, it now starts to go down. And it oscillates. It never blows up. It accumulates stuff integrating, and then it loses it. Accumulates it, loses it. So this goes up and down. It never becomes negative if I did it this way, but it oscillates. So it's bounded. It doesn't go off to infinity, and that's why I have an input and I have an output. And the input and the output then have an amplitude ratio. That's kp over omega t, and there is a phi minus. There's things like minus pi over 2. Are there any questions on that? Okay, well that brings us to the end of the hour. Are there any questions? Okay, I neglected to give you homework last time. I will give you the homeworks today. Again, if we're looking ahead towards exams, when we finish chapter 6, which is the chapter we're in now, the material on the next exam will cover all of that. Once we finish chapter 6, after that comes control. So we're going to have an exam before we actually start getting to control. These are all the techniques. Any questions on any of that?